Hi, my name is Breaking Hawks, and this is my Lab 3 macroscopic view of DC and RC currents. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, measure actual voltage and potential difference, as well as examine the behavior of both ohmic and non-ohmic resistors and capacitors. This lab allowed me to simulate creating different circuits with various resistors and capacitors to learn how each affects the workings of the circuit overall. I was able to examine the relationship between potential difference and various sections of a circuit, as well as how the ratio between potential difference and initial voltage changes over time as the capacitor is discharging. I found that initially the computed RC value based on the slope of the natural log of potential difference versus time was very close to the RC value of the circuit, though over time the values became rather different. The most important physics concepts for this lab would be the loop rule, which focuses on energy conservation and states that for a complete loop, the potential difference overall is equal to 0. We also use the node rule, which states the overall current going into a point will equal the overall current going out. I first predicted the currents I1 and I2 were equal to 0.02 amps using the loop rule and the given values of resistance. Then I created the circuit using the circuit connection kit as seen to the right. This showed me that my prediction for the currents was correct as witnessed by the readings of the ammeters. When one ammeter was reversed, I got the same readings. And then when the top ammeter was replaced with a voltmeter, the top ammeter read 0 amps and the voltmeter read -3 volts. I then took voltmeter readings of the potential difference at various points around the circuits going clockwise. The current remained at a constant 0.02 amps as read by the ammeter. These values for potential difference make sense because when added together they sum to 0, which is what should happen for a closed circuit. When you attach the voltmeter and the ammeter, the ammeter reading doesn't change because the voltmeter should act as a perfect resistor with 0 resistance. However, the ammeter is not a perfect resistor, so when a second ammeter is added in parallel to the 100 ohm resistor, it decreases the original ammeter's reading due to the increase in resistance created by the second ammeter being added into the current path. I found that when I calculate the resistance of specific sections of the circuit using my measurements for potential difference in current, they were pretty close to the circuits given the values for resistance. Moving on to RC circuits, when charging a capacitor, current flows into the capacitor, and while discharging, the current flows out of the capacitor. Both of these actions causes the light bulb to go brightly and then dim and then go out as the capacitor either reaches peak charge or empties of charge completely. This is due to the current's flow stopping after charging or discharging occurs. I then measured the potential difference as the capacitor charged and then took the ratio against the initial voltage. Then plotted the natural log of the absolute value of that versus time. Compare my calculated value of 1 over RC, which is the slope of the graph, versus the value for 1 over RC of the circuit. I found that for 1 to 7 seconds, my computed 1 over RC value was 1/5, which is close to the circuit's 1/6. However, over the entire graph, from 1 to 20 seconds, my computed value was 1 over 13, which is a significant difference from the 1/6. As for the what-if questions, if we had used an actual ammeter instead of an ideal simulated ammeter, a real ammeter would be even less perfect and therefore add additional resistance. If we used a real battery to charge a real capacitor with no resistor in the circuit, the capacitor would not be fully charged almost instantaneously like our model predicted. The wires and batteries used would not be perfect and would add their own resistance to the circuit, thereby increasing the time to fully charge the capacitor. That's it for my lab. Thanks so much.